Hey guys, Marcel here with another video, and in this video we're going to prove that the cyclotomic polynomials that we defined in the previous video are irreducible. Okay. So first we're going to talk about what it means to be irreducible. So a polynomial f of z with integer coefficients is said to be irreducible over has v over z if it cannot be expressed as a product of two non-constant polynomials in z of z. Okay? Well, what does that mean? You guys have probably seen this before, but for example, x squared plus 5x plus 6, this is a polynomial with integer coefficients. It is not irreducible. It is reducible because you can express it as x plus 2 times x plus 3. Okay? So those are two non-constant polynomials, so that's a reducible polynomial. On the other hand, x squared minus 2 is irreducible over z, because if you wanted to factor it, you would need to introduce real numbers. So this is x plus square root 2, x minus square root 2, right? Okay. So, well, what we're going to try to prove in this video is that the cyclotomic polynomials are irreducible, and we introduced them in the previous video, and we also computed a few examples. So, for example, 1 of z, the first cyclotomic polynomial is just z minus 1. The second is z plus 1. The third is z squared plus z plus 1. I'm not wrong. Maybe there's a minus somewhere. I think we computed them way the heck up here. Oh, where's that? Z squared plus z plus 1, yeah. And 4 of z was z squared plus 1, and so on. Okay. And we're going to prove that all these are irreducible. If you look at these, you can kind of, well, the linear ones are obviously irreducible. This polynomial here, you can stare at these and figure out that, like, for example, 4 of z is irreducible because its roots are plus minus I, right? And yeah. Okay. Let's see. Okay, so first we're gonna need a lemma. So we are actually going to have to work over FP in our proof later, that cyclotomic polynomials are irreducible. So we need a lemma in FP. FP, of course, is the finite field with P elements. So let Fz be a polynomial with coefficients in FP. Okay? Then f z to the p is equal to fz all to the p in fp of z. Okay? Now, we need to break down the statement a little bit. This is not saying that these are equal as functions from fp to the complex numbers, right? Because that would be immediate. We have Fermat's little theorem that says a to the p equals a in z. In FP, right? So that would be immediate, right? Because then fz to the p, well, that's the same as f of z, and then f of z is the same as f of z to the p. So, I mean, as like functions, this is sort of trivial, but what we're actually saying is that these two polynomials are equal in the ring of formal polynomials. They have the same coefficients. Okay? All right, so we are going to use this fact later on, but it's not just a direct a direct consequence. So what's the proof? Okay, so we just expand. So let f of z equals a0 plus a1z plus all the way up to amz to the m. And we have fz to the p is equal to, obviously, a1z plus amz to the m all to the p. Now, this is the multinomial theorem. So we know the binomial theorem, right? If you have just two, you have a sum and you want to take it to some power, there's a binomial coefficient that shows up. Well, here there's a multinomial coefficient that shows up. So we want all k1 up to km that add up to p. And then we have this multinomial coefficient, so k1, km. When p equals 2, this is just the binomial coefficient because we want k1 and k2 to add up to p. Well, that's like p and then p minus k, right? Product of j equals 1 to m aj z to the j to the kj. What is this saying? Well, we want to figure out every way you could possibly, you need to pick p of these, right? Every time you have the product of p copies of this polynomial, so there's going to be p of these terms combined together to make this product. Okay, so they have to add up to p, and so k1 is how many times the first term, or k1 is how many times this term it shows up in the product. Okay, and then you need to take a sum over all possible multinomial coefficients. Okay. All right. So okay. Now we're gonna break down what this means, and I should just write this out. Like, what is this thing? Okay, this thing is equal to p factorial over k1 factorial. K2 factorial all the way down to km factorial. It's the number of ways of splitting p things into boxes, like size k1, size k2, all the way up to size km. Okay, so we want p things, we want to pick. Okay, I guess, honestly, I might have made a mistake here with the m. It might be 0 up to m. Have I actually made a mistake? Is that right? No, I don't think so, because we want, yeah, if you have a 0 p times, j doesn't show up at all, right? So, right, it's just the constant. Zj to the kj. I think this is correct, okay? But you can, if it's wrong, you guys can put it in the comments or something, and then I'll have to deal with the consequences of that later. Okay, but okay, let's look at this coefficient. So unless sum ki equals p, okay, so the only way, there's a p up here, and all of these numbers are smaller than p. They add up to p, remember. So these numbers are all smaller than p, which means you get a bunch of numbers in the denominator that are all smaller than p, and there's a huge number of them multiplied together, but they're all smaller than p, which means we have a p in the numerator and there's no p in the denominator to cancel it out. So unless sum ki equals p, there is a p in the numerator and none in the denominator. Okay, and what does that mean? That means that, well, remember, p is equal to 0 in fp, which means this whole thing is 0. Okay, so what we've shown is that p, k1, km is equal to 1 if ki equals p for some I, and 0 otherwise. Okay, so this is perfect because, look, what we had was a sum of so many different things, but now we only really need to look at, there's only m cases, right, where k1 is equal to P, or K2 is equal to P, or Km is equal to P. So the sum becomes a lot more manageable. So let's write this. So sum, let's just write Fz to the P is equal to this sum. So it's I equals 1 to M, okay, AI Z to the I, to the P, right? So also in the product, everything disappears except one of them, right? Everything else is just one. There's just the, right? Everything else is, all the other kj's are 0. So it's just 1. And then you just have one AI Zi to the P. Okay? Now we use Fermat's little theorem. So we have I equals 1 to M. This is AI to the P. Zi to the P, right? Now, Zi, the I is inside the brackets. So this is equal to sum I equals 1 to N AI because of Fermat's little theorem. Anything to the Pth, anything to the Pth power is the same thing. And then we can flip here, so we get Z to the P to the I. But of course, that is just F Z to the P. Okay? The polynomial F had coefficients AI, and we're plugging in Z to the P. So that's exactly what we wanted to show. Okay, so much for that. Next, we're just going to prove that the nth cyclotomic polynomial is irreducible. So theorem, let's write out the nth I'll just remind you what the nth cyclotomic polynomial is. It's phi n of z, and it's a product over all omega, primitive roots of unity, z minus omega. Okay, not all the roots of unity, but the primitive nth roots of unity. The nth cyclotomic polynomial is irreducible over z. Okay, so proof. Okay, so it's a proof by contradiction. So suppose towards a contradiction, that phi of n, phi sub n is equal to fg for some non-constant polynomials f and g in integer polynomials. Okay. Then what this means is then the primitive roots of unity can be partitioned into disjoint A and B. So all the primitive roots of unity are they're in either A or B, and they're both non-empty. Disjoint non-empty A and B, such that f of z is equal to product of all omega in A, z minus omega, and then g of z is the same thing but with B. So equals product over all omega in B, z minus omega. Okay. Now, since any two primitive roots are powers of one another, there is omega in A and m, in integer m, such that, I should say integer powers of one another, but that goes without saying, and m such that omega to the m is in B. Okay? Now, we're not quite done. We can actually specify that m be prime. Okay? Not right away, not like this, but of course we need a prime because, well, should be hinting that we need a prime because we had a lemma about finite, fields of prime order up above. So we need to kind of pull a prime out of somewhere. Okay, so let's factorize. Factorize m equals p1, p2, all the way up to pk. Okay, so these are, maybe the pi's are repeated, it doesn't matter. And we set omega 0 to be omega, and then omega I to be equal to omega p to the power. I should write this. Okay, this is really bad writing because it's crashing into stuff on top, but omega of p1 all the way up to pi. Okay, so what that means is that omega I minus 1 to the power pi is omega I. Okay, so in particular, omega k is equal to omega to the p1 all the way up to pk, which is the same as omega to the m. Okay? Now, so, I mean, what this means is omega 0 is an a, right? Omega 0 is just omega, which is an a, and omega sub k is omega to the m, which is in b. So let j be the smallest index such that omega j is in b. So that has to be the smallest one because omega 0 is in a and omega k is in b, so that has to be the first time that you get into b. Then set omega prime to be omega j minus 1 and p to be pj. Okay, we have omega prime in a and omega prime to the power of p in b. Okay, so we've done this whole rigmarole to get the same statement up here, except now omega is in a, omega to the m is in b, but m is prime. Okay, I mean, it's a different omega, it's a different n, but okay, and we've called it then omega prime and p. All right, so far so good. Okay, so that means omega, so if omega prime's in a and omega prime's in a and omega prime to the power p is in b, omega prime is a root of f, z, and a root of this polynomial g, z to the p. Okay, because omega to the p makes this 0. All right, so now if we let h of z be the GCD of f and g, okay, we can write h of z, just because you can always do this with the GCD in a Euclidean domain, right? You can, h of z is equal to f of z. You just keep running the division algorithm until you get the GCD, and then once you get the GCD from all your steps, you can reconstruct this. I'm sure you've seen this somewhere. F of z rz plus g of z sz. Okay, and it doesn't matter what rz and sz are. What I just want to say is that omega prime is a root of fz, and oh, sorry, there's a p here. Okay, omega prime is a root of fz, and omega prime is also a root of g z to the p. So it's a root of this whole thing, right? It makes h of z 0. So omega prime is a root of h z, and in particular, h z is not 0, okay, or not constant. Let's say, not let's say it, like it's not constant, because a constant polynomial has no roots. Okay, so h of z is not constant. Now we move to fp of z. Now we move to fp of z. Okay, and here, remember we proved above, h of z to the p is equal to h z to the p. That's the lemma that we proved earlier. And also there's this, it's the same thing, zn minus 1 power p is equal to z and p minus 1. Okay, so we applied the lemma twice. Okay, now since phi n of z is equal to fz times g z to the p, and this thing in zp you can do this, right? Is that right? Sorry, this is, I did this wrong. Okay, so f phi n of z to the p is the same, is f z to the p g z to the p, right? That's from our assumption in the very first line. Now you pull the p out of one of them, okay? But you leave it there for the other. Okay, and we know that h divides this, so h divides this, and h also divides this, okay? If h divides this, then h to the p divides this whole thing, and then h also divides this still, so h of z to the p plus 1 divides phi n z to the p. Okay, does that make sense? So we're just counting divisors here, counting how many times h divides this polynomial. Okay, now since phi n z to the p divides z n p minus 1, okay, because remember phi n of z is a product of that z minus omega for all the primitive roots of unity. Z to the n minus 1 is a product over all the primitive, all the roots of unity, all the nth roots of unity, primitive or otherwise. So obviously this divides that. And we talked about this a lot in the previous video. Well, this thing is just z n minus 1 to the p, right, by the lemma. Okay, so h z to the p plus 1 divides, so it's transitive, right, divides z n minus 1 to the p. Okay, now because h to the p plus 1 divides this polynomial, it's an n, to the p times, that means that you can't actually have this unless, and so this implies that hz squared divides zn minus 1. I don't really need the brackets actually, because it's not to the p anymore, okay? Because you can't take, okay, like just stare at this and it'll make sense, right? You can't have it any other way. If it didn't divide z to the n minus 1, then you wouldn't, taking p powers, yeah, once you strike away all the other ones, you're left with a 2. Like, you kind of need to have like a 2p here, sort of, okay? Just because of integer powers. Okay, I did not explain that very well, but it certainly follows. Okay. All right, so now let's call this polynomial p. So we have, since h squared divides p equals h squared q for some q in, sorry, fp to z. Okay, and so let's take the derivative of this. So p prime is equal to the product rule, right? So 2h prime, leave q fixed, plus you leave h squared fixed, and then you take the derivative of q. Okay, so p is divisible by h, but p prime is also divisible by h. There's an h here and an h there. Okay, so both p and p prime are divisible by some non-constant polynomial h. Okay, so what is p? I mean, this means, you know, p is z n minus 1, and p prime is n z to the n minus 1. Okay, but now we're going to get to a contradiction, because on the other hand, we just let n minus 1 be the inverse of n in fp, the multiplicative inverse, and we can just divide those polynomials. We can take z to the n minus 1 is equal to, well, it's n to the minus 1 z times nz to the n minus 1, right? Because these cancel out, and then you get power, plus minus 1, okay? And then we have to do the next one, right? So nz to the n minus 1 is equal to, what have I written here? Is equal to minus 1 minus nz to the n minus 1 plus 0. And then we reach 0, which means this is the GCD, and we can just make it positive. So the GCD of zn minus 1 and nz to the n minus 1 in fp of z is 1, right? It's a constant, well, at the very least it's minus 1. It's a constant polynomial. And that's a contradiction, right? So this contradiction shows that phi n of z is irreducible. Okay, because, well, what caused this entire bit of nonsense to begin with is that we supposed that you could factorize 5n into fg, and then we arrived at this contradiction. Okay, so that's the irreducibility of the cyclotomic polynomials. All right, see you next time. Next time we will do, we'll introduce Vandermonde matrices. Yes, we're on our road to proving Tau's uncertainty principle.